In this video, we're going to be looking at two things, the Polygon Sum and the Exterior Angles Theorem. Assuming that the interior angles of a quadrilateral are constant, okay, quadrilateral would have 4 sides and 4 angles. Assuming that the sum of the interior angles are constant, what would that sum be? Well, assuming that the sum of the interior angles is going to be constant, what we can do is think about one of our most basic quadrilaterals, which would be a square. And in a square, each of those 4 angles would be 90 degrees. So if we multiply 4 by 90, we get 360 degrees. We get 360 degrees. And of course, that would be true for a rectangle because all the angles there are also 90 degrees. But does it hold true for all types of quadrilaterals? Would that be true for a trapezoid? Would it be true for a parallelogram? Would it be true for a rhombus? Would it be true for any random type of quadrilateral, anything that has just 4 sides on it? Okay, well it is, and we're going to prove that it is. Given quadrilateral QUAD, let's prove that the measure of angle Q plus the measure of angle U plus the measure of angle A plus the measure of angle D, that would be the interior angle sum, is equal to 360 degrees. All right, to show that this is true, what we're going to do is start with a picture. Once we construct the picture, then we will formally write up a 2-column proof to go along with it. Okay, so we're going to begin with just any random quadrilateral. Okay, that means I'm not attempting to measure any of the lengths that I have here. However, what I am going to do is leave some space open over here so that I can write my 2-column proof. All right, so it almost looks like I have a bit of a trapezoid off to the side here, but since these 2 sides aren't parallel, it is actually just a random quadrilateral. All right, so let's call these angles Q, U, A, and D. Okay, we want to prove that if we add up all the angles together, we get 360 degrees. Okay, the trick to doing this is to use the Triangle Sum Theorem. Okay, let's actually divide it. Yeah, we'll divide it this way. All right, what I'm going to do is draw a diagonal here, and that diagonal is going to break it into 2 triangles. Okay, in this triangle, I still got angle Q, but up here at angle U, I don't know if that's been bisected. Okay, what I'm going to do is write down angle 1 and 2, so it doesn't get complicated later. Okay, the alternative would be to call this angle QUD and call that angle AUD. Much easier if I just call it 1 and 2. Okay, at the bottom, I'm also going to have 3 and 4 for the same reasoning. Okay, so according to the Triangle Sum Theorem, this triangle that we have here, QUD, that triangle would add up to 180 degrees. And AUD would also add up to 180 degrees. All right, and what's important to mention here is that if you add all the angles together, they are the angles of the quadrilateral. Because the angles A and Q, those happen to be part of the quadrilateral, and then 1 and 2, together they're actually angle U, and 3 and 4 together are actually angle D. So all of the angles that I show here, which is a total of 6 of them, will have a grand total of 180 plus 180, which is 360, and this would be true. So it's not important what type of quadrilateral you have. You could do this with literally any quadrilateral and show that you get 180 and 180. All right, so now our job is to write this up as a 2-column proof. All right, so to start things off, we do have a quadrilateral, but I'm not going to mention that. What I'm going to do is say that we're going to draw the diagonal UD. We're going to draw that. Okay, and that is called an auxiliary line. All right, so now that we have that, we can go ahead and identify angles 1, 2, and 3 and 4. Okay, and I'm going to write it this way. The measure of angle 1 plus the measure of angle 2 is equal to the measure of angle U. And along with that step, I'm also going to write the measure of angle 3 plus the measure of angle 4 is equal to the measure of angle D. which is the angle addition postula. We'll abbreviate this time. All right, and then for 3, what I'm going to do is go back to the triangle sum, stuff that I talked about there. Okay, the measure of angle Q plus the measure of angle 1 plus the measure of angle 3 is going to be equal, not to a measure, we know how much it actually equals, because you have a triangle here, that'll be 180 degrees. And likewise, the measure of angle A plus the measure of angle 2 plus the measure of angle 4, those 3 there, are going to equal 180 degrees. And that we call the triangle sum. Technically called the Triangle Sum Theorem. We'll call it triangle sum here. Okay, 4, I'm going to add all this together. Okay, I'm going to add the left sides together, I'm going to add the right sides together, which this part's going to get a little bit confusing here because I don't really have a whole lot of space to write. Okay, but the measure of angle Q plus, and I'm going to attempt to be strategic about how I write this. So literally I'm going to take all 6 of these together. Okay, but I'm going to write in this order. I'm going to say the measure of angle Q plus the measure of angle 1. Then I'm going to skip over to 3 and go to angle 2. Plus the measure of angle 2 plus the measure of angle 3. Actually, nope. Want to use A. This is all about organization. Plus the measure of angle 3 plus the measure of angle 4, and those could be flip-flopped if I wanted, is going to equal 360 degrees. Okay, so I took everything on the left, grouped those together, took the 180 and 180 together and got 360. And for step 5 here, because it was stated earlier that these two, angle 1 and 2, are the same as U, I can substitute right here. And in addition to that, we got 3 and 4 is the same thing as D. So there's 3 and 4, which is going to be D. And if I put it all together, I've got the measure of angle Q plus, this is going to be the measure of angle U, plus, that one is, oh, here we go. That'll be A. So that was Q, that's U, that's A, plus angle D is going to be equal to 360 degrees, which is exactly what we wanted to show there. All right, and then for reasons, because I didn't write the last couple of here, 4 is going to be substitution. 4 is going to be substitution. Nope. Got ahead of myself. 5 is the substitution, where I replace that with the A. So 5 is substitution. And 4 is just the addition property of equality. All right, so here's the neat thing here. The same method that I used to figure out the sum of the interior angles of a quadrilateral, I can use to figure out the sum of the interior angles of any polygon. In particular, let's look at a pentagon, a 5-sided figure. All right, again, as long as it has 5 sides, that's all we're looking for here. Okay, so the sides don't need to be congruent. Just has to have 5 sides, just has to have 5 sides to be called a pentagon. Okay, and then using diagonals, I could break here, okay? These 3 angles here, let's put little arcs in them. Well, okay, I'll put little arcs in them, but they're not all the same size, so don't read that as congruent symbols there. Okay, but these 3 together are gonna add up to give you 180 degrees. And then if I divide up here, I get 3 more angles that I have in there. Let's just use a different color for them. Okay, those three are going to add up to 180 degrees. And then these three will also add up to 180 degrees. We can actually make three triangles. And again, all the angles that I've marked here are all actually part of the angles to the Pentagon. I mean, that is actually one of them. That would be another one there. But these two together are going to make that angle, and these two together will make that angle, and the three that I have up here are going to make that angle. Okay, so within all my 180s, I don't have extra angles that don't apply to the actual Pentagon. Okay, so we can conclude that if we took 180, multiplied it by 3, we'd get 540 degrees. And for this, we're not going to make a two-column proof because it would basically be the same proof that we just did for the quadrilateral, except you have an extra triangle, which is just going to make the whole thing a little bit longer. All right, so what we're going to do next is summarize our findings, okay, and eventually come up with a formula that we could use to figure out the sum of the interior angles of any polygon, whether it be a pentagon, octagon, decagon, and so on, okay? All right, so if you had a three-sided figure, which is just called a triangle, we already proved that's 180 degrees when you add up all the angles inside the interior sum. Okay, if you have a quadrilateral, four-sided figure, 360 degrees. We just proved that. And five-sided figure, pentagon, is 540 degrees. Okay, and as you move through the number list that you have here, you're going to realize that we're just adding on 180 degrees. Okay, and then visually that would make sense because what we were doing was creating another triangle, which is worth 180 every time we added on a side. Okay, so you could go ahead and assume now, or if you want, you can draw the picture just to verify to yourself that this would be true. A six-sided polygon, which is called a hexagon, is going to be 540 plus 180, which is going to be 720. Let's make that look like a 0. All right, and the pattern is going to be consistent. I'll go ahead and just keep adding that on. Okay. Not going to write it here because n is going to represent any number of sides. All right, a seven-sided figure actually has two different names that you can use. The most common is a heptagon. The second is called a septagon. And if we add 180 onto 720, we get 900 degrees. An eight-sided figure called an octagon is worth 1,080. A nine-sided figure is called a nonagon. The sum for that is going to be 180 onto this, which would be 1,260. Then a 10-sided figure called the decagon is going to be 1,440. All right, and then at the very end here, the n is going to represent any number of sides. Okay, so what if you were asked to figure out the sum of the interior angles of a figure that had 30 sides, right? You've got this pattern that you can do, but it might not really work out good to keep adding 180. Okay, so what you can probably already figure out is that if you were to multiply some number by 180, you could get to that right amount that would be there. The thing that you need to be careful of here is that you are not multiplying the number of sides by 180. That's not what you're doing. For example, if I take 6 and multiply that by 180, I'm going to end up over here for the octagon. Okay, and then if I took 8 and multiply that by 180, I get 1440. I'd be over here. I'm actually off by 2. So the formula, it is going to be 180 multiplied by something, but it's going to get multiplied by not the number of sides, but 2 less than the number of sides. Okay, so for example, let's go to our quadrilateral. Okay, it's not going to be 4 times 180 because that gives you 720. But if I decrease the 4 by 2, so take 180, multiply that by 4 minus 2, that does give me 360. Okay, and let's check it out for the heptagon here. If I take 7 and minus 2, I get 900. For example 1, the sum of the interior angles of a regular polygon is 180 degrees. Okay, regular polygon, that means that all of the side lengths are the same size, which also means that all of the angles are the same size. All right, so if the sum of the interior angles of a regular polygon is 1800, what would be the measure of each interior angle? Okay, well, we can use this formula here. 180 multiplied by n minus 2 is going to have to equal 1800. It's going to have to equal 1800. And then from this formula, what we can figure out will be the number of sides that we have. Okay, we'll divide by 180, which is going to give us 10. Okay, 1800 divided by 180 is going to leave you with 10. We'll add the 2 onto that, which is going to give us 12. A 12-sided figure is called a dodecagon. That would be called a dodecagon. Okay, but to officially answer the question, what is the measure of each interior angle? We would take the 1800 total that we have, divide that by 12, and get 150. All right, for the second part of the notes, what I wanted to do was talk about exterior angles. Okay, so given any polygon, let's go with a pentagon. I just always think those are a little bit more interesting to look at. All right, so suppose we've got a pentagon here. We got one really short side there. All right, exterior angles. Try and clean up these edges just a little bit. All right, an exterior angle is formed when you extend out one of the sides past its vertex. Okay, so that would be an exterior angle. Go ahead and call that one 1. All right, and then the nicest looking picture is going to be if you sort of make it look like a spiral. So we got 2. That'd be 3. This will be 4. You could extend that direction, and that size angle would actually be the same as 4. Just go ahead and make that as a note beforehand. All right, and then last, you get 1 here. All right, so the number of exterior angles is going to correspond to the number of sides, which also corresponds to the number of vertices that we've got. Now, in our hope to learn a little bit about exterior angles, what we're going to do is make some observations about this stuff. All right, first, notice that each exterior angle is a blank to an interior angle. For example, angle 2 is adjacent to an interior angle. Okay, not the word that I'm looking for here, not to say that it's adjacent, because beyond that, we've got this extra property that together they make a straight line, which means that they are supplementary. So notice that each exterior angle is a supplement to an interior angle. Together, they're going to make 180. All right, second observation. In an n-gon, that means whatever number of sides you have. In this case, we've got 5 sides. In an n-gon, there are n linear pairs. So referring back to that, right there, that would be a linear pair. That would be a linear pair here, here, and here. Okay, so in a pentagon, you're going to have 5 linear pairs. All right, so then in an n-gon, whatever that might be, whether it be an octagon or a decagon or whatever, the number of linear pairs that you would have would be n. You would have n of them, which means that you get a total of blank degrees between interior and exterior angles. Okay, every linear pair is worth 180 degrees. Okay, so that would give you 180 times n. In this picture, it would be 5 times 180 because you would have 5 linear pairs, which are each worth 180. Okay, but we're going to do this in terms of variables. We're going to let n represent any number of sides so that we can extend this idea beyond a pentagon. All right, third observation. The sum of the interior is blank. Okay, well, we just proven earlier that the sum of the interior is going to be 180 multiplied by n minus 2. And given all these observations, we should be able to figure out the sum of the exterior angles. All right, to do this, let's start with a word equation. Okay, if I took the sum of the interior and I added it to the sum of the exterior, I get the total. Right, all the angles inside plus all the angles outside is going to give me some grand total. That grand total is 180 times n, right? You have n linear pairs, so you get 180 times n. The interior, we know an expression for that one, which is this. So we've got 180 n minus 2 plus the exterior is going to be equal to 180 n. All right, so if I want to get the exterior angles, that would be the exterior angle sum. That would be equal to the total 180n minus the interior all right, and with a little bit of distribution here, we get 180n minus 180n. This will distribute over, the negative is going to distribute over. You're going to get a positive 360. And these two cancel out, which means that the sum of the exterior angles is 360 degrees. And what's interesting about that is it's a constant. It means that no matter the number of sides that you have, the number of angles that you have, if you were to take the sum of the exterior angles, it is always going to be 360. All right, for example 2, what you're asked to do is measure the exterior angles of your polygon and verify that it does measure to 360. Okay, for that question, I'm not going to go through the demonstration of it. You should have your own picture. If you did draw it with a straight edge, you could practice using your protractor to verify that the angles do in fact add up to 360, or incredibly close to it, because there's always that potential that the way we measure is just slightly off. For example 3, we're told that we have a regular polygon. That would mean that all the side lengths and the angle measurements are congruent. We're also told that an exterior angle would be 72 degrees. That would mean that all of the exterior angles are 72 degrees. Okay, what is the measure of each interior angle, and what is the name of the polygon? The exterior angles are always going to add up to 360. So if I take 360 and I divide it by 72, that will actually give me the number of exterior angles. So 360 divided by 72 gives me 5. We get 5 there. All right, now that will actually already answer the second question that we have here. If you have 5 exterior angles, you have a pentagon. You have a pentagon. Now, what would be the measure of each interior angle? Okay, well, the exterior angles are the supplements to the interior. So if I take 180, subtract 72, we get 108.
Wait, what?